Okay, so I wanted to try to record problems 18 through 24 and post those so that hopefully it'll help you understand how to work those problems. So let's get started. I'm going to start on number 18. And number 18 says that you have a television set that draws 2.55 amps of current, and that the voltage is 120 volts. And it asks you for the resistance of the set. Well, R is equal to V over I, as you learned in lab. So V is 120. I is 2.55 amps. So when I did that, I got my R to be 47.06 ohms. And then I said, well, part B wanted to know how much power does the set use. Well, power is V times I, or you can use I squared R or V squared over R. It doesn't really matter. 120 volts times 2.55 amps is 306 watts. And then it says how much energy does it burn if it uses 5 hours every day. And we're going to use it for 30 days. Then we're going to run our television 150 hours. And energy is power times time. Power needs to be in watts, so I divided by 1,000 and got 0.306 kilowatts. I'm sorry, power needed to be in kilowatts. And hours was 150. So to get kilowatt hours, which is a measurement of energy, I multiplied those together, and I got 45.9 kilowatt hours. And then they want to know how much is it going to cost to operate my TV for those 30 days at 5 hours a day. So I said, well, the cost is 5.5 cents per kilowatt hour, or $0.0555 per kilowatt hour. And I want to run it for 45.9 kilowatt hours. So the electrical company is going to charge me $2.52 to watch my TV 5 hours a day for 30 days. So that was pretty straightforward. Number 19. Number 19 was about a capacitor. So you have to go back and remember that we know that the charge on a capacitor, Q, is equal to CV. The capacitance was given to you as 2.50 picofarads, which is 10 to the minus 12th. And the voltage that it was charged to was a 12-volt battery. So Q is equal to CV, so 2.5 times 10 to the minus 12 farads times 12 volts is 30 times 10 to the minus 12 coulombs, or you could say that's 30 picocoulombs, or you could write it as 3 times 10 to the minus 11th, same thing. So you can express it any of those ways. All right, number 20. Number 20, you had a parallel plate capacitor. The area was 1.9 centimeters squared. The distance of separation was 0.0850 millimeters. Epsilon naught was a constant. So you had to go back and think about the unit before this one, where we said C was equal to epsilon naught A over D. Now you cannot leave the area in centimeters squared. Sorry. So I said, well, I know there are 100 of these, and every one of these, I'm going to square that puppy and square that one. So when I did that, I got 1.90 times 10 to the minus 4 meters squared for my area. My distance of separation was given to me in millimeters. I cannot leave it in millimeters. I have to put it in meters, so I needed to divide by 1,000 to get it there. So that gave me 8.5 times 10 to the minus 5 meters. So C is equal to, well, that's 8.85 times 10 to the minus 12 coulomb squared over Newton meter squared. I'm going to multiply that by an area of 1.90 times 10 to the minus 4 meters squared. And I'm going to divide that by 8.5 times 10 to the minus 5 meters. So when I did all of that, I got my capacitance to be 19.8 picofarads, or you could write it as 1.98 times 10 to the minus 11th farads. Either one will work. All right, 21. 21 was the one that we were asked to find the energy stored in a capacitor. We had to go back and remember the energy is 1/2 CV squared. The C was given to you as 112.5 microfarads. The voltage that it was charged to was 9 volts. So I said, well, the energy stored is 1/2 C V squared. So when I did that, I got energy to be 4.55 times 10 to the minus 3rd joules. All right, 22. 22, you had a circuit. There was a resistor here, then there were 3. And then there was a resistor right in here. And I left that out, so let me draw that for you. Battery. So this one up here was 58 ohms. Call that R1. This one was 75 ohms. R2. R3 was 65 ohms. R4 was 45 ohms. And then this one down here was 35 ohms. And they were all hooked up to a 15-volt battery. So I immediately saw this as a group of 3 parallel. So I said 1 over RT is equal to 1 over 75 plus 1 over 65 plus 1 over 45, and I used my x to the minus 1 key on my calculator, and I got RT to 19.63. And then I said, well, I'm going to come over and redraw that as 3 simple resistors in series. There's my battery. That's still 58. This is now 19.63. And this one is 35. So then I just added up 58 plus 19.63 plus 35. And that gave me the total RT as 112.63. Okay, so I finally got the total resistance, and that was one of the things they wanted to know. Then they wanted to know the total current. Well, IT equals BT over RT. So I had 15 volts over 112.63 ohms. And that gave me 0.133 amps. And then the hardest part was they wanted to know what was the current right here. Well, I said I3 is equal to V3 over R3. Well, I don't have V3, but the cool thing is I know the voltage here, here, and here is the same, so if I can find the voltage here, then I will know V2, V3, and V4. So V2 equals V3 equals V4. To get that, it's going to be I times R. So I'm going to say that my I that went into that group was 0.133 amps. My total resistance was 19.63 ohms. So if I multiply those together, that gave me a voltage of 2.61 volts. And that was V2, V3, and V4. So now I can finally go over here and say, well, 2.61 volts divided by 65 ohms gives me I3, and I3 was 0.04 amps. So I went through that quickly. You might need to go back and watch a couple of times, but if you think about what I did, this current was 0.133, and it had to go through this entire group, which was 19.63, so I multiplied the total current times the total resistance to find the voltage for that line, and each one of those is 2.61 volts. All right, let's take a look at actually I'm going to stop and then I'll record 23 and 24 separate.